All right, today we're diving into a problem that has, I'm not kidding, stumped physics students for decades. It's a real classic, pulled from one of the most notoriously tough problem books out there. So let's get right into it. So if you've spent any time in a physics or engineering program, you've probably seen this book. Yep, it's Irodov's Problems in General Physics. This thing is legendary. The problems in here, they're not just about plugging numbers into formulas. They're designed to really make you think. And today, we're going head-to-head with problem 1.55. So what's so special about this one? Well, at first glance, it looks pretty straightforward. But trust me, there is a very, very clever trap hiding in plain sight. Okay, let's read this out and really break it down. We've got two solid bodies, and they're rotating around axes that are perpendicular to each other. Now, here's the key phrase. Their angular velocities, omega-1 and omega-2, are constant. And the goal? Find the relative angular velocity and the relative angular acceleration of one body with respect to the other. And this right here is where almost everyone gets snagged. That little word, constant. It's both the most important piece of information and the biggest trap in the whole problem. So your brain immediately goes, wait a minute, omega-1 is constant, omega-2 is constant. That means no acceleration, right? It seems so obvious. The relative angular acceleration has to be zero. I mean, it just makes sense. And that, my friends, is exactly the mistake this problem is built to make you fall for. So, to figure out why that gut instinct is wrong, we need to do something physicists are always doing. We have to change our perspective. Literally. The answer is a big, resounding no. The relative angular acceleration is absolutely not zero. The whole secret to cracking this thing is to stop being a spectator. You have to stop watching from this stationary lab frame, as we call it, and actually jump into a rotating reference frame. Let's try a little thought experiment. So first, picture yourself just standing in a lab, watching these two objects spin. That's our starting point. Now for the fun part. Imagine you could shrink down and sit on body 2. You're now spinning right along with it at angular velocity omega-2. So, what does the world look like from your new spinning point of view? Everything else, the lab, the floor, and crucially, the rotation axis of body 1, it all seems to be rotating around you. And this is the whole idea behind a rotating reference frame. It's exactly like being on a merry-go-round. From your perspective on the horse, you feel like you're sitting still, but the whole park is spinning around you. Now apply that to our problem. A vector that's perfectly constant in the lab, like the angular velocity vector for body 1, suddenly looks like it's changing from your new spinning viewpoint. And what do we call a change in velocity over time? That's right, it's acceleration. All right, now that we've got our heads wrapped around that big concept, let's get back to the math. We'll start with the first part of the question, finding the relative angular velocity. And you'll be happy to know, this part is actually pretty simple. Yeah, whenever you see the words relative velocity, it should be a big flashing sign that says vector subtraction. We want to know the velocity of body 1 as seen from body 2. So all we have to do is take the velocity of body 1 and subtract the velocity of body 2. So let's get our coordinates straight. Since the axes are perpendicular, it's easiest to just align them with our x and y axes. So we'll say omega-1 is along the x-axis, which makes it 3.0 I, and omega-2 is along the y-axis, so that's 4.0 j. Then our relative velocity, omega-rel, is just omega-1 minus omega-2. That gives us the vector 3.0 I minus 4.0 j. Okay, so now we need the magnitude of that vector, the actual speed of this relative rotation. And since our components are nicely perpendicular, we can just bust out the good old Pythagorean theorem. We're just going to take the square root of the sum of the squares of the components. So we've got the square root of 3 squared plus negative 4 squared. That's the square root of 9 plus 16, which is the square root of 25. And that gives us a nice clean 5.0 radians per second. Bam! Part 1 is done. Okay, deep breath. Now for the main event. This is the part that makes this problem famous, or infamous. Let's find that relative angular acceleration. So let's circle back to that big question from the beginning. We know for a fact that the magnitudes of the velocities are constant. So where in the world is this acceleration coming from? And here it is, the big reveal. Remember our thought experiment? From the spinning perspective of body 2, that omega-1 vector, well, its length isn't changing, but its direction is. It's constantly rotating. And you have to remember, velocity is a vector. It has magnitude and direction. So a change in direction is an acceleration, period, just as much as a change in speed. Now, luckily for us, physics has a perfect mathematical tool for calculating this very specific type of change, the vector cross product. The rate of change of that omega-1 vector, which is our relative acceleration, is calculated by taking the cross product of the frame's own rotation, which is omega-2, with the vector we're observing, omega-1. And the easiest way to visualize this calculation is by setting up a little 3x3 determinant. You put your unit vectors I, j, and k across the top row. The second row is for the components of the first vector in our cross product, omega-2, so that's 0, 4, 0. And the third row is for the components of the second vector, omega-1, so that's 3, 0, 0. Now, you can go ahead and calculate that determinant, or you can just use the formula for the magnitude of a cross product. It's just the magnitude of the first vector times the magnitude of the second times the sine of the angle between them. In our case, that's 4.0 times 3.0 times the sine of 90 degrees. Since the sine of 90 is just 1, the answer is a clean 12.0 radians per second squared. And there you have it, a non-zero relative acceleration. So, we did it. We cracked the Irodov code on this one. Now, let's take everything we just learned and put it into a neat little toolkit that you can use the next time you run into a tricky problem like this. All right, let's wrap this up with the key takeaways. First, and most importantly, remember the trap. Constant angular velocities do not mean zero relative angular acceleration. It's a classic trick. Second, the secret weapon is always to shift your perspective into a rotating reference frame. When it comes to the math, remember that relative velocity is just straightforward vector subtraction. And finally, the big one. Relative acceleration comes from the changing direction of a vector as seen from that rotating frame, and your tool for that is the cross product. It really makes you think, doesn't it? How many other things in physics seem simple on the surface, but when you look at them from a different, rotating point of view, they reveal a whole new layer of complexity.